So today I'm going to be talking about the Friis formula, or Friis, I'm not exactly sure how to say it. And this formula is essentially a way of saying if you've got a transmitting antenna with a certain transmitted power, let's call it PTX, and you've got a receiving antenna somewhere else that's got a certain received power, PRX, we want to find, given the transmitted power, and the distance between these antennas, let's call it R, um, how much power is received by your antenna on the right? Well, in my opinion, the easiest way to analyze this problem is just with a picture. So we know that the transmitting antenna is transmitting out spherical waves. Now, they're not even over the sphere. The electric field varies with the angle, but the waves themselves are purely spherical. So we've got a wave here, and then as it propagates outwards, it becomes larger. As it propagates further outwards, the sphere becomes larger. And when it gets to our receiving antenna, it's even larger. And we say that everything we're doing is under the assumption that by the time the power, the spherical waves gets to our receiving antenna, it looks and acts like a plane wave because it's a really big sphere. So if we're only looking at a small section of that sphere, it looks like a line. Well, okay, all we need then is to find the power density at this area. Well, we can just calculate that directly. For an isotropic antenna, it's just the power of the transmitter divided by 4 pi r squared. So that would be the power density at the receive antenna. And if we want to know not just the power density, but how much the receiver is able to handle, then we can use this concept called effective aperture, which is essentially if the antenna were just a perfect net that could catch all the power that flowed through it, that would have a certain value. And we say that that's the effective aperture, which is an area. So it's to find the power received, it's nothing but the power density at that location, which is PTX over 4 pi r squared, times the effective aperture. And we're almost done. Like that's the majority of the formula. All the conceptual work is done. The only thing we need to take into account now is that our antennas typically aren't perfectly isotropic radiators. So their radiation level or their directivity or gain, whatever you prefer to use, varies with angle. So we know for a dipole antenna, the radiation pattern looks something like this. So that's our dipole antenna, where the radiation varies like sine theta, where theta is this angle from the z-axis. And this is just our little antenna in red. Now, we know that we've defined the gain previously, which incorporates the directivity and the efficiency of the antenna as the amount. So let's evaluate the gain at a specific theta. Let's say theta equals pi over 2. The gain at this location is nothing but the total radiated power density. So let's call it S rad, divided by the power density of an isotropic radiator, S isotropic. And that takes into account as well the antenna efficiency. So it's when you measure it, you just define it this way. So if we go back to our previous problem and we forget that gain varies with angle, and we pretend that, well, since this antenna is reasonably far away from the transmitting antenna, then this angle here, let's call it phi, this angle is small. And so the amount that the power density varies from this point to this point is small enough to be neglected. If that's the case, then all we need to do to find the power density at this location is multiply by the gain. So our Friis formula just gets modified with a g. And that's the entirety of the formula. It's incredibly simple. It allows very easy and quick evaluation given antenna parameters that are typically given, such as the gain, effective aperture, and the transmit power. And you don't need to remember the formula if you remember this picture. Just imagine a transmitting antenna with spherical waves propagating outward, and the receiving antenna is just acting like a net that catches all that power on its way outward. And if we assume that it's far enough away, then the gain or the power density doesn't vary much from the top to the bottom of this effective aperture. And all we need to do to find the power density relative to an isotropic radiator is, by definition, multiplying by the gain. So this is well, by definition, multiplying by the directivity, but gain takes into account efficiency of the radiator. So this is our final formula. The received power, PRX, is equal to, and I'm going to write it a little differently as it's written above. It's equal to the transmit power you feed into the antenna, times the effective aperture divided by 4 pi r squared. The reason I like writing it this way is because this is essentially how much area or what percentage of the area our antenna is effectively covering, multiplied by the gain. And that's our final formula. Now, we haven't gone over how to find the effective aperture, but that's something that can be done relatively straightforwardly.